So let's go over this problem first. So find the limit if it exists. Okay, when I look at this problem, I can tell this is the limit doesn't exist. The limit does not exist. The reason is it's a polynomial degree, the numerator and denominator both are 4, they're equal. So that gives you some freedom to get different limits around different passes, okay? So if the numerator, the degree is higher than the denominator, then more likely it's going to be 0, the limit, okay? But otherwise now it's, so you can show that the limit doesn't exist. So you can along the x-axis, for example, okay? Along the x-axis, so this is the point, right? Approach at 0 and 0, right? Okay, then this function is going to be always 0 because the y value is 0, so it's 0. It's approach 0, okay? Yeah, okay. Then you cannot do that along the y-axis; you still get the same result. So you have to choose the line in the middle. Along the line, y equals x. Okay. So then x, y both are going to be t and the t approach 0. Okay. This is a so the parameter is t. Then the expression is going to be t squared and t squared, t to the 4th power, t to the 4th power. After simplified, it's going to be 1/2 because it's always equal to 1/2. So that means the function, the value function does not approach any finite number. Okay, so this implies x does not approach any fixed number. Okay, as x, y approaches 0 and 0.
Do we have to switch it to t, or can we just put everything in terms of x? Yeah.
They can put, yeah, you can let y to be x, change y to the x. Doesn't matter. The parameter is not, can still be x or can be y. Okay, so that means the limit, therefore the limit does not exist. You have to point it out that, okay? So this is about the problem. So today, that's a section 14.5. Well, we cancel class, right? But I look at my schedule. There's not much impact on my schedule. I have a 2 review class for test number 1, so I'm going to have 1 review class for test number 1. Okay, that's the only change. Okay, so this is about general for functions for quantities depend more than 1 variable. So let's recall the general we learned in calculus 1. Okay, if you have 2 variables or even more, right? You begin with a y. Okay, you try to differentiate y with respect to x. Okay, so that's the relationship between, you know, you have a bunch of variables, so x and y, right? For x and y, you want to find the derivative of y with respect to x. That's called the rate of change in y with respect to x, assuming y depends on x. But it's possible y depends on u depends on x. Then the general says that it can be computed using by this formula, right? And you can add more variables. So y depends on u depends on x, and maybe u depends on v depends on x. So you can keep it going, and du and dv and the dv dx. So you get longer. That's what called a chain rule. Okay. How about a quantity? How about the quantity? You know, both z like depends on x and y, and both x and y depends on another one or two variables or even more. Okay, so now we assume that z depends on x and y. I just put this, and both x and y depends on one parameter, depend on t. So z depends on x and y. Instead of one variable between z and the t, there's a two variables between the b and t, right? First of all, z depends on t. Very simple. You find the derivative of z with respect to t. But the dependency on t is not direct. Is not directory. So it depends on x. You know, like this. This is a picture. It depends on x and y that both depends on t, right? Right. And in this case, we can find the derivative of z with respect to t, the rate of change, using the following chain rule. But this, okay, because you insert two variables, okay? So what I'm going to do is it's going to be the partial derivative of z with respect to x. Then this is the derivative of x with respect to t. Right? Then you have to find the partial derivative of y with respect, partial derivative of z with respect to y. Then here's dy dt. Okay, so that's the chain rule. But it's also possible x, y both depends on another two variables. How can I write on the chain rule? Okay, so here we assume that z depends on u and the v. But before that, and there's two variables between z and u and the v. Okay, z depends on x and y, and then x and y depend on u and the v. How about like that? Okay. So there was two variables between z and a pair of the variables u and v. So how can I use a picture here? So first of all, yeah, it depends on x, it depends on y, but both depends on two variables. Okay, that's a picture. So I'll give an example, right? For example, z equals, okay, z equals x times y. Now z depends on x, y, but x depends on u and the v, like u square plus v square, and y is going to be u, just u, right? Then you can get z equals u square plus v square times u, right? So z depends on u and the v, but also z depends on x and y. Okay, so that's a picture. So how can I find the derivative of z, the partial derivative with respect to u? Right? You can find the derivative directly if you're able to express z in terms of a u and v. But you can also use a chain rule. Right? The chain rule here is okay. So that's a chain rule. So you just differentiate z with respect to all the possible values, intermediate variables, x and y. Okay, but then when you differentiate with respect to x, you have to, don't forget, you have to differentiate that variable with respect to u. Okay, and similarly, if you want to differentiate z with respect to v, you have to differentiate z with respect to all the intermediate variables, that's x and y. So partial derivative z with respect to x, but don't forget you have to differentiate x with respect to v. Okay, so those are called the chain rule. Now we can verify that using examples. This is a formula we're going to study. Right. Whenever you want to insert the variable, you make sure you multiply the derivative with respect. Like now, when you differentiate z with respect to x, you have to make sure differentiate x with respect to u, because your original variable is u. Okay, so so that's it. So let's take a look at some examples. So this is a z equals sine x sine y. Okay, and the x is going to be square root t, y is going to be 1 over t. Okay, all right. In other words, z is going to be sine square root t and sine 1 over t. Right? So we want to find out the derivative of z with respect to t. You can find this relation first, then you differentiate, right? Well, yeah, if you find the formula for in t was for z, then you just differentiate directly by the product rule. So that is going to be the derivative of the first term and times the second term plus the first term, first fact derivative of the second, right? Then cosine becomes cosine, and then don't forget the derivative of square root t. Okay, and here sine square root t, and that's cosine 1 over t. As a derivative of 1 over t is negative 1 over t squared. So this is the answer. We can also use a chain rule to differentiate. You have to find the derivative of z with respect to x in dx dt. Okay. Okay. You probably get the same. You will get the same result. So partial derivative of z with respect to x. Look at z cosine x sine y. So just cosine x, right, and sine y. Then you have to differentiate x with respect to t, which is going to be that. And partial derivative z with respect to y will be sine x cosine y. And then we differentiate y with respect to t is going to be negative 1 over t squared. So if we compare both sides, you get same result. Exact same result. Just replace x by square root t and y by 1 over t. Okay, so next problem. So the next problem here is a z. Z equals the square of x e to the xy. X equals 1 plus st. Y equals s squared minus t squared. So z is a function of st. Yeah, we want to find out partial z was partial, the partial derivative of z with respect to s. All right. So, you can express z as a function of st. So just square root of 1 plus st and e to the, it's pretty complicated, 1 plus st and s squared minus t squared. Then you differentiate, okay? But I don't want to do that, it's pretty complicated. What I'm going to do is I use the formula, the chain rule. Okay? The chain rule, if you have two intermediate variables, you should get sum, get two partial derivatives here. Okay, it's not just product. Now, as the derivative of z with respect to x, it's a little bit complicated. Differentiate x, it's going to be square of x is going to be this, and plus the derivative e to the xy, e to the x times y with respect to x will be y. So that's going to be x and y, e to xy. Okay. Then you differentiate x with respect to t with respect to x. That's just t. Okay. The next one is derivative of z with respect to y is just x times x e to the x times y. So you have to find the derivative of y with respect to s, which is 2s. Okay. So that's enough. Okay. Now you can substitute 1 plus st for x, s squared plus minus t squared for y. But just make it more complicated. So this looks fine. This is a derivative. Maybe at the end you can say that where x is going to be 1 plus st, y be this. Okay, that's enough. Okay, even when you write a program like a Maple to do computation, you just define x to be 1 plus st. You don't need to put everything into the final expression. So then the expression looks better, simpler. Okay, so at the end you just say where x equals 1 plus st. Then this should be the answer. You cannot simplify it further. All right, so the next part. So t equals v and 2u plus v, and u equals pq square root t square r, and v equals p square root q and r. Complicated. Yeah, find the partial derivative of t with respect to t. Okay, when p equals 2, q equals 1, r equals 4. Okay, what does that mean? First of all, t is given by this relatively simple expression, v over 2u plus v. So this is a picture, t depends on U and the V. But both U and the V depends on PQR and PQR. So finally, T is a function of PQR. So we want to find out the rate of change of T in T with respect to P. Okay, so the partial derivative T with respect to P is just rate of change in T with respect to P when Q and R fixed. Okay, so you can substitute the expression for U and the expression for V into the formula. Then you get a direct, you get a formula for T in terms of PQR, but that's a very complicated expression. So I prefer to use a chain rule to find the derivative. Now, when you use a chain rule, okay, there's 3 layers here. T is on the very top, UV in the intermediate variables, and PQR at the bottom. They are equal. PQR equal position. So this should be the partial derivative of T with respect to U, then partial derivative U with respect to P. Okay. So you view T as like a grandfather and U and V are parents, and then PQR 3 kids. Okay, think about this relationship. Okay. Yeah, so when you differentiate T with respect to P, so make sure all the 2 parents are included. Okay, UV. So now let's find the derivative of T with respect to UV, with respect to U and with respect to V. It's pretty complicated, so let's do this first. Right? According to the chain rule, right? The quotient rule. This is a V and 2U plus V. Right? So it's going to be 2U plus V squared. Then the derivative of V with respect to U is going to be 0, so don't worry about that. Minus V times the derivative of 2U plus V is just 2. Right? It's not too bad. So it's negative 2V, 2U plus V squared. Okay. So this one will be a little bit complicated. So 1 times 2U plus V minus V times the derivative of denominator, which is only 1. So you will get 2U, just 2U. V is gone, right? V minus V is gone. Okay, so you guys, those 2. I also have to find out, let's go back, how does it depend? Oh, PUV depends on, maybe on P is fine, it's easy. So, yeah, list all the possible derivatives. Okay, the derivative U with respect to P is just Q square R. The derivative of V with respect to P is just a square and Q and R. Okay, so now we are done. Okay, we write down we already have formula, the product. So UV, so negative 2V, 2U plus V squared, and that's the Q square R plus 2U, and that's QR. Okay, so this is a formula. We have to evaluate. Okay, when you evaluate, when P equals when p equals 2, q equals 1, I equals 4, okay, what do you get? You have to still have to find out u and the v, right? So in that case, u is going to be 2 square 2q and the square root of r, so that's 4. V is going to be 2 square root of q and r, so it's 8. Okay, so now you plug everything into all those two into the above formula. It's negative 2v 8. Denominator is 2u. 2u is 8. 8 plus v8, so it's 16 square. Q is 1 square root of 4 plus 2u. U is 4. And here still 16 square. And square 1 times. Okay. I think that that's going to be 0. Why? The numerator here is 4 times 8. And here, 4 times 8. So it's going to be 0. So it's the derivative 0. Okay. Yeah, you don't need to get the final expression in terms of a PQR for the partial derivative. You still can keep a UV, but you just need to find the corresponding value for UV, then you simplify. So this is one type of problems. And the next type of problems we're going to do is use the implicit differential method to find the derivatives. Okay. So here y equals cosine x times 1 sine y. Okay, we are going to find the partial derivative. No, actually, this is not partial derivative. So derivative y with respect to x. This is a problem from calculus 1. Right? You only have 2 variables here. So y depends on x. So dy over dx is just rate of change in y with respect to x. So how do we do that? We just differentiate both sides with respect to x. But when we're doing that, let's see, what is equation 6? Yeah, there was a specific equation. Oh, okay. Okay, so idea is, you can differentiate both sides, okay, with respect to x. Let's finish that use a traditional method. Right? Derivative, right, with respect to, x. So here, I think it's a channel. This is by the channel, right? Cosine becomes sine x times y. Then you have to differentiate x times y. So it's by the product rule, it will be like this. Right? And this side is going to be cosine y and dy dx. So now you get negative y sine x times y, and you move the other term to the right hand side. So this will be x times sine times xy, and cosine y. You take factor the derivative out. Okay, so these 2 terms will be moved to the other side. Okay, so the derivative is going to be negative y sine x times y, and x sine x times y plus cosine y. Okay. Okay, so we got this. Now we suppose, yeah, let's look at the general case. Suppose you have two variables. They are given by this equation, so they're related. You can have two functions, just put together. So x and y satisfy this equation, right? So you're going to use a channel, right? So you differentiate f with respect to x, and that's going to be 0, right? So when you differentiate a function, if you use a channel, you have to differentiate the first fact. Let's use this notation. So dx dx and fy. Let me put more details here. Dx over dx. That's a channel. Dy over dx. Right? So dx over dx is just 1. So dy over dx can be written in the form of like that. Right? Okay, this is going to be 1. Yeah, the channel says that, you know, sometimes we do not, we just give an expression there. Okay, so sometimes we say z, you know, yeah, sometimes we can say z equals capital Fxy, and what is, right? If we want to differentiate with respect to x, okay, then yeah, differentiate with respect to x, or with then just like it, right? So you then the partial derivative with respect to x and partial derivative with respect to y. No, that's a different. Yeah, I'm not going to talk about that. Let's apply the above formula to solve the following problem. I have a so this is just only one variable, two variables. Now, if you have 3 variables, you have 3 variables x, y, z equals 0, right? So now you can view z as a function of a y, x and y. So you want to find the derivative find the partial derivative of z with respect to x and the partial derivative with respect to y. And here viewing z as a function of x and y. Right? In many cases, you cannot solve for z. Okay? What are you going to do? So you differentiate both sides with respect to x. All right. So y is independent of x. Okay. So z depends on x, y. So only z is a function for x. Okay. So when you differentiate that, you have to use a channel. Right? Well, this is going to be 1. and this is going to be 0. Right? So partial derivative of z with respect to x will be negative. Yeah, this is the z. Okay. And similarly, you can get the partial derivative of z with respect to y. Yeah, let's look at the following problem. W is going to be x, y plus yz. Oh no, let's try a different problem. This is a, let's look at, yeah. So we are given e to the z. Yeah, e to the z and equals x times z. Okay. Find the so here z is a function of x and y. Z depends on x and y. Okay. You don't need to know the above formulas. Okay, you just view z as a function of the y, and x and y are independent variables. They're independent each other. Okay. Then you want to find the partial derivative with respect to x. So this implicit differentiation. Okay. So what you can do, yeah. Here, yeah, we view z as a function of x and the y. Okay. And the y, x and the y are independent of each other. So there's no relationship between x and y. Okay. When you solve for z, you get the function of x and y. Yeah, is yeah. So z is going to be x. That's why, you solve the above equation, but it's not, you cannot solve it. You just say the solution exists. So we want to find a z. How can I find the partial derivative with respect to x? It's an implicit differentiation method. So you differentiate both sides with respect to x. Right? Yeah, you differentiate both sides with respect to x. So when you differentiate e to the z, right? So just differentiate e to the z and then partial derivative z with respect to x, just like the usual. Okay? And here you will get the product. All right, it's a product. But remember, y is independent of x. So this is going to be y times z. Suppose you have 3 terms. Okay? Okay, but y is independent of x, so this term is 0. And this is going to be 1. So it's going to be yz plus x times y of that. So now you have 2 terms containing the partial derivatives. Okay, you move this term to the left, e to the z minus x times y. Okay, so you solve the problem. Okay, so the answer will be these are just implicit differentiation. Implicit differentiation. Yeah, let's take a look at the next problem. We have x squared minus y squared plus z squared equals minus 2z equals 4. Find the partial derivative of z with respect to x. Right. We can also find the partial derivative of z with respect to y. So here, z can be viewed as a function of x and y, but you don't need to find the expression. So z depends on two variables, not just only one. Okay. So we just differentiate both sides with just partial derivatives, right? It's a similar, yeah, partial derivative. Right. So the derivative of x squared with respect to x is 2x. The second term is 0 because y is independent of x, and plus 2z. And here 2 partial derivative with respect to x, and it's again 0. Okay. So now you get 2x plus 2z minus 1 equals 0, and you can easily solve for the partial derivative. Okay, it's going to be, if you change the sign, it's 1 minus z, and here's x. Pretty simple form. So there is a proof for the channel. The proof is just use a definition to take the limit, then you get the channel. Okay. Now let's try one more problem, then we take a quiz. Okay, so this is the next part, the last. Let's have a quick review. So if u equals x to the fourth times y squared, here's z cubed. Okay, so u depends on x and y, and x, y, z. So x is going to be RSE to the t, y equals RS squared e to the negative t, and z equals r squared s and sine t. Okay, we want to find out the partial derivative u with respect to s. Okay, when I equals 2, s equals 1, and t equals 0. Now, to do that, I also needed to find out at that moment what is the x value. When when r equals 2, s equals 1, I think x is just equal to 2. 2 times 1 e to the 0, which is 2. Y is going to be 2, 1 square e to the negative 0, it's still 2. So the z value will be 2 square, 1, and sine 0, which is 0. Okay, so this is a corresponding value for z, x, y, z. So you have one variable u, and it depends on 3 variables, but these 3 variables also depends on another 3 variables. So dependency is pretty complicated. Okay? But anyway, u depends on ist, and you're trying to find the partial derivative u with respect to s. Okay. So according to the formula, you don't need to find the expression in terms of ist for u. Okay, you can use So by you can use the chain rule. Okay. So when you use the chain rule, the intermediate variables are x, y, z. So you have to differentiate u with respect to all those variables. Okay. So now let's find the partial derivative. Let's do together. Okay. The partial derivative u with respect to x is 4x cubed y, nothing else. And then partial derivative x with respect to s, just I e to the t. Then the partial derivative u with respect to y, that's going to be x to the fourth power 2y z cubed. And the derivative y with respect to s is going to 2r s e to the negative t. And the partial derivative u with respect to z will be 3y squared z squared. And the partial derivative z with respect to s is r squared sine t. So you can see that is a chain rule, although the expressions will be complicated, but still in the very simple form. Okay. Then you evaluate at this point. Okay. R equals 2, s equals 1, t equals 0. Then you have to find out the corresponding value for x and y. So it's 4, 2 cubed, y is 2. Okay. And r is 2, e is to the 0. Okay. And here x is going to be 2 to the fourth power. 2 and 2. Z is going to be 0, so don't worry about the third term. 2, 1 e to the negative 0. And the third term is 3, 2 square, z is 0. So don't worry about the third term. Yes, sine. Okay. And yeah, then you can simplify it. How many 2's here? 2 plus 3, 5, 5 plus 2 to the 7th. Okay, let me check the second part. You have a 4 plus, 2 to the 6. Yes, 2 to the 6. Yeah, so you can simply write it this. Yes. Right. So this is it's about the chain rule. Okay.